Bismillahirrahmanirrahim. Assalamu alaikum. Today we will cover photoelectric effect. It is a very simple process, but it involves a lot of physics. It is because of this that Einstein won the Nobel Prize for quantization of light. Einstein proposed that emitted electrons were knocked out of metal by bundles of light called photons. Einstein speculated that when an electron collides with photon, the electron takes energy of photon and flies off. This process is called photoemission, and the electron ejected from the metal are called photoelectrons. The process is very simple. Light is made up of tiny packets of energy called photons. When the light strikes the metal surface, the energy of the photon is transferred to the electron in the middle, and if the energy of the photon is sufficient enough, the electron in the metal will escape with certain amount of kinetic energy. This process is instantaneous. The energy of incident electromagnetic wave is equal to energy required by the electron to escape the metal surface plus kinetic energy of the free electron. Therefore, the condition for photoelectric effect is that the energy of the incident wave must be greater or equal to the energy required by the electron to escape the metal surface. As a particle proposed by Einstein, light carries energy proportional to the frequency of the electromagnetic wave. E is equal to h nu, where E is the energy of the photon, h is the Planck's constant, and nu is the frequency of the electromagnetic wave. If we strike a ping pong ball to the wall, nothing will happen to the wall. If we strike a bowling ball to the wall, it will cause a dent in the wall. The reason is that the bowling ball has more energy than the ping pong ball. Similarly, if we strike electromagnetic wave of low energy to the metal, no electron will be emitted. On the other hand, if we strike electromagnetic wave of high energy, then the energy of the photon will be transferred to the electron, and the electron will also possess some kinetic energy. The kinetic energy of the electron is equal to the energy of incident photon minus the energy required by the electron to escape the metal surface. The absence of lag time confirms that light is behaving like a particle in photoelectric effect. When radiation strikes on target material, electrons are emitted instantaneously. The photoelectric effect helped propel the then emerging concept of wave-particle duality in the nature of light. Our photoelectric effect equation is h nu is equal to phi plus half mv square. H is the Planck's constant, nu is the frequency, pi is the work function, m is the mass of the electron, and v is the velocity of the electron. Work function is defined as the minimum work needed to remove the electron from the metal surface. So the maximum kinetic energy of the photoelectron is the energy of the photon minus the work function, because the electron has to do work to escape the potential from the metal. In other words, the photoelectron outside the metal doesn't have the same energy as the incident photon because it has used some of the energy to escape the metal surface. Let's put it all together. Energy of photon is equal to work function of metal plus kinetic energy of electron. Energy of photon is equal to h nu, where h is the Planck's constant and nu is the frequency. Work function is equal to phi is equal to h nu naught, where nu naught is the threshold frequency. It is the lowest frequency below which the photoelectric effect does not occur. Kinetic energy of electron denoted by Ek is equal to half mv square, where m is the mass of the electron and v is the velocity. The condition for photoelectric effect is that the energy of photon must be greater or equal to the work function, which means h nu must be greater or equal to h nu naught, which means that the frequency of the photon must be greater than the threshold frequency. Let's define photoelectric effect more precisely. Photoelectric effect is the emission of electron from the metal surface when the light with frequency above the threshold frequency is incident on it. For any given material, there is a minimum threshold frequency below which emission of photoelectron stops, no matter how high the intensity of light is. This is the apparatus used to observe the photoelectric effect. Electromagnetic waves enter through the quartz window and strike the metal plate P. Metal plate P is negatively charged since it is connected to the negative terminal of the battery. Collector C is positively charged since it is connected to the positive terminal of the battery. A voltmeter is connected in parallel to determine the battery voltage. When electromagnetic waves strike metal plate P, the photons transfer the energy to the electrons, and this results in the emission of electrons called photoelectrons. The photoelectrons rush toward the collector since the collector is positively charged, and we get photoelectric current measured by the ammeter connected in series. We will use variable batteries so that we can change the voltage from 0 to higher values. In the beginning, we have zero potential. We open the quartz window and let the light of constant frequency fall on the plate P. If the frequency of light is greater than the threshold frequency of the metal plate P, electrons will be emitted and we will observe non-zero ammeter reading. A variable potential difference is applied between plate P and collector C. Since the collector C is positively charged and plate P is negatively charged, the electrons emitted from plate P will be attracted to collector C. If we increase the potential difference between plate P and collector C, eventually all electrons emitted from plate P will reach the collector C. The photoelectric current will reach maximum. If we increase the potential difference between plate P and collector C, the photoelectric current remains constant. This maximum value of photoelectric current is called saturation current. When electromagnetic waves of certain frequency above the threshold frequency strike the metal plate P, we observe ammeter reading and hence the photoelectric current, even when the battery potential is zero. As we increase the battery potential between plate P and the collector C, the photoelectric current increases. Eventually, a point is reached when all the photoelectrons emitted from plate P reach the collector C. This is called the saturation current. High intensity of light means more photons of light strike plate P, more electrons will be ejected from plate P, and the photoelectric current will increase. Higher the intensity of light, higher the saturation current. Hence, we observe the photoelectric current is proportional to the intensity of light. To calculate the stopping voltage for the electrons, we need to reverse the terminal of the battery, which means that the positive terminal of the battery is connected to the plate and the negative terminal of the battery is connected to the collector. The maximum kinetic energy of the photoelectron is found to increase with increase in the frequency of incident light, provided the frequency exceeds threshold frequency. The maximum kinetic energy is independent of the intensity of light. The stopping voltage refers to the potential difference required to stop electrons from moving between the plates and creating a current in photoelectric experiment. When light is incident on plate P and the energy of photon is greater than the work potential, photoelectron is emitted as discussed previously. Stopping potential is the minimum negative potential given to the plate of the photoelectric tube for which the photocurrent stops or becomes zero. Stopping potential is a measure of maximum kinetic energy of photoelectrons being produced by incident radiation. Therefore, we get the relation K max is equal to EVS, where K max is the kinetic energy of electron, Vs is the stopping potential, E is the charge of electron, EVS is equal to energy required to stop the electron. For negative potential difference, as the potential becomes more negative, the value of photoelectric current decreases and becomes zero at the stopping potential. For positive potential, the current steadily grows until it reaches the saturation current. The saturation current is when all electrons from the plate P are reaching the collector C. Further increase in the battery potential beyond this point does not increase photoelectric current at all. As the frequency of incident light increases, the kinetic energy of photoelectrons increase. Since photoelectrons have higher kinetic energy, greater stopping potential is needed to make them stop. Since the intensity of light is constant, the number of photons striking the metal plate is same. Therefore, saturation current, that is due to photoelectron reaching the collector and passing through the ammeter, is the same. Now let's keep frequency of incident light constant. Therefore, energy of incident photon is constant. The maximum kinetic energy of photoelectron is same, and so is the stopping potential. However, now we are increasing the intensity. The greater the intensity, more photons strike the metal plate. Therefore, more photoelectrons will be emitted. More photoelectrons will reach the collector and pass through the ammeter. Therefore, higher the intensity, higher will be the saturation current. Let's cover the flowchart of what we have learned so far. Let's consider the case that we increase the intensity of electromagnetic wave and keep the frequency of electromagnetic wave constant. Since the intensity of electromagnetic wave is higher, the number of photons will be higher, the photoelectric current will be higher, and so will be the saturation current. Since we are keeping the frequency same, the kinetic energy will be same and the stopping potential will be the same. Let's consider the case that we increase the frequency of the electromagnetic wave and keep the intensity of electromagnetic wave a constant. Since the intensity of electromagnetic wave is a constant, photoelectric current remains the same and the saturation current remains the same. If we increase the frequency of electromagnetic waves, the energy of photon increases, which means kinetic energy of photoelectrons increase, which means that the stopping potential increases. Let's test our understanding. On the same graph, draw in blue, what would graph look like if we decrease the intensity and increase the frequency of incident photons? Since the intensity of the incident light decrease, the number of photons in the incident light also decrease, which means that the fewer photons strike the metal plate and fewer electrons will be emitted. Fewer photoelectrons will reach the collector current. The photoelectric current will decrease. The saturation current will also decrease. Since the incident light has a higher frequency, photons have a higher energy. Photons of higher energy strike the metal plate. Electrons that are emitted will have higher kinetic energy. This means greater stopping potential is required to stop the photoelectrons from reaching the collector and for photoelectric current to become zero. The equation for photoelectric effect is H nu is equal to phi plus Ke. H nu is the energy of photons, H is the Planck's constant, nu is the frequency of photon, phi is the work function, Ke is the kinetic energy of photoelectron. H is the Planck's constant and has a value of 6.63 into 10 raised to power minus 34 joules second. To find the value of H in electron volt second, we'll divide H by the charge of the electron. Therefore, H is equal to 6.63 into 10 raised to power minus 34 divided by the charge of electron, that is 1.6 into 10 raised to power minus 19. We get the value of H is equal to 4.14 into 10 raised to power minus 15 electron volt second. Another useful constant is hc, where h is the Planck's constant and c is the speed of light. H is equal to 6.63 into 10 raised to power minus 34 multiplied by speed of light, that is 3 into 10 raised to power 8 meter per second. We get the value of hc in joules meter to be 1.989 into 10 raised to power minus 25. To convert it into electron voltmeter, we will divide it by the charge of the electron. Therefore, Hc is equal to 1.989 into 10 raised to power minus 25 divided by 1.6 into 10 raised to power minus 19. It is equal to 1.240 into 10 raised to power minus 6 electron voltmeter, which means it is equal to 1240 electron volt nanometer, where nanometer is 10 to the power of minus 9. Work function phi is equal to h nu naught, where h is the Planck's constant and nu naught is the threshold frequency. Kinetic energy of photoelectron is equal to half mv square is equal to EVS, where E is the charge of the electron and Vs is the stopping potential. Therefore, the photoelectric equation is equal to h nu, which is the energy of photon, is equal to h nu naught, that is the work function, plus kinetic energy of photoelectron, that is equal to EVS, where E is the charge of the electron and Vs is the stopping potential. If we rearrange the equation, we get the stopping potential is equal to h nu divided by E minus h nu naught divided by E. If we plot the stopping potential versus frequency, we get a straight line. When stopping potential is equal to 0, nu is equal to nu naught, which means frequency is equal to threshold frequency. And when nu is equal to 0, stopping potential is equal to minus h nu divided by E. The x-intercept of the graph is the threshold frequency. Kinetic energy of the electron will be 0 at the threshold frequency. Hence, stopping voltage will be 0 at the threshold frequency. The y-intercept is equal to the work function of the metal in electron volt. For any frequency less than threshold frequency, it is like electron is in deep hole. As the frequency goes from 0 to higher values, the electron is lifted higher out of the hole until finally at its threshold frequency it's out. The slope of the graph is always a constant, h over E, where h is the Planck's constant and E is the charge of the electron. The value is 4.14 into 10 raised to the power minus 15 electron volt second. The work function and threshold frequency for different material is different. For instance, work function of sodium is 2.4 electron volt and work function of copper is 4.6 electron volt. However, slope of stopping voltage versus frequency of incident light is a constant h over E for all materials. May Allah bless us all. Thank you for watching. Allah Hafiz.